Hi guys, welcome to your Chapter 9 Part 2 video. We're going to do a couple of things with this video. First of all, given that this chapter focuses on, and it's titled Regression Wisdom, we're going to talk a little bit about the steps that you need to go through when you make a regression line, the things you need to be paying attention to, and we're going to talk a little bit about lurking variables as well, which is just something to consider as you do your regression analysis. It's related to the fact that with a scatter plot, as we've talked about, you're not looking at cause and effect per se. Maybe, but you don't know that. At the very least, you know you're looking at association between variables. All right, so the second slide, let's start by rehashing and dropping Algebra 1 assignments all over the place. Let's start by rehashing the conditions to be met when considering regression line. Okay, so first of all, this goes back to Chapter 7, maybe? Chapter 8, somewhere in there. This is the quantitative variables condition. Okay? And that is just to say that you're not going to build a regression line that takes numerical input, gives you a predicted numerical output, unless you can be darn well sure that both your variables are quantitative. If you've got qualitative data masking these quantities, be careful. The regression line is probably not the tool to use. All right, second piece here. You've got to make sure that the straight enough condition has been met. Okay? And we'll talk about how we can, the tools we have to check that here in the next little piece of this slide. But in essence, does the data follow a straight line? If not, there is probably a more appropriate tool out there to use. In Chapter 10, we're going to talk about how we can, when the data is not straight, we can re-express it by doing a transformation, a scale, maybe taking the square root, taking the log of the data to make it straight so we can use this regression tool that we've been spending chapters and chapters upon now. Third piece here, outliers condition. And that's really the heart of Chapter 9 right here. We've been spending time talking about points with high leverage, points with high influence, high residual outliers, and whether or not they're going to be influential for the regression line. Outliers are something you got to pay attention to. Remember that if you've got an outlier that is clearly influencing the regression line in your scatter plot, you need to make sure that you remove it, and if you remove it, that you are saying that it's been removed from your regression line analysis. Or alternatively, if you're choosing to keep it because it highlights something that you feel is important, you need to make note of that too. Outliers are things that need special consideration because they're not following the trend in the rest of the data. All right, so there are the conditions that have to be met when we need to build a regression line. Here are the tools, mostly from your calculator, that you can get to help you analyze those conditions and whether or not they've been met. So the steps to build your regression line are the following. Firstly, you need to look at your scatter plot. That is the first thing you are, so where's my @ sign there? Look at your scatter plot. Okay, what is that going to allow you to do? Well, really, it's going to allow you to check, at least on some level, all three of the above conditions. In looking at your scatter plot, you're going to hopefully be thinking about whether or not your quantitative variables condition has been met. You will certainly be able to check the straight enough condition. And lastly, to some extent, you can see the outliers, okay? All three of those things you can get from the scatter plot. If you do nothing else, and I don't know why you would do nothing else, but let's say you're pressed for time on a quiz or a test, at the bare minimum, check your scatter plot before you build your regression line so you can know you're in the right ballpark. Secondly, you need to look at your residuals plot. That was first shown to you guys in Chapter 8, resids plot. I talked about that being a magnifying glass on how the data is relative to the regression line we want to build through the data. It tells us how far off the points are from the line we're trying to build. And in the process of building your residuals plot, you're doing two things. You're checking the straight enough condition, and you're also checking the outliers condition. The residuals plot will make outliers abundantly clear because they should be far removed from the rest of the residuals in your residuals plot. All right, so both of those graphical tools are hugely important to build your regression line. And then third thing that we're going to do, even though I bet a lot of you guys don't see value in this yet, but you certainly will in Chapter 10, you're going to consider, at least look at it, don't necessarily report it, but consider your R-squared. Remember that R-squared talks about the appropriateness of your regression line. In more detail, it tells us R-squared is technically the percent of the fluctuation or the variability that we see in the true y values, not the predicted. It's the percent of the variability you see in the true y values that the regression line explains. Now, obviously, an R-squared of 100% is rare. That would mean that all of your data falls on the regression line and that all of the y values that are truly in the data matches up with what the regression line predicts the y values to be. That's rare. You're not going to find lines in the real world, usually, okay? So, there's a recap. There are the instructions you need to follow largely right here. These are the instructions you need to follow and the steps you need to take in following those instructions to make sure that your regression line is good. Let's check out a problem in a context. We'll look at lurking variables in this context. I think it'll be better than making it an abstract lesson. Data from the World Bank for 26 Western Hemisphere countries can be used to examine the association between female life expectancy and the average number of children women give birth to. There are, I think, 2 rows of 13, 26 countries in all. So you're seeing births per woman on average for each of these countries from around the world. Oh, here we go. And the average life expectancy, or I guess life expectancy is already an average, so kind of redundant, but your life expectancy in each country as well. So we clearly have 2 quantitative variables, births per woman on average in each of these countries and life expectancy for each of these countries. So your respondents, in some sense, are the countries, right? All right, in A, they say create a scatter plot relating these 2 variables and describe the association. Some of you guys, I bet, are forgetting, just as when you describe a distribution, you're looking for shape, center, spread. Association, closely linked. You've got 3 things you need to describe in your scatter plot. They are strength, direction, and form, okay? So I have entered all of these births per woman values into L1, all the life expectancy values into L2, and this wabbit. Okay, let's close that. I'm trying to beat the bell. It's going on 2:55, and I'm trying to make sure I get this done by that point. I guess you can see the time. Come on, wabbit. Oh, there it is. Okay, cool. Oh, that table's driving me crazy. We got our scatter plot on. L1 is our X list, L2 is our Y list. Let's zoom stat this puppy, and we've got one clear outlier. How can we figure out what the outlier is? Easiest way is to trace, go over to that. You can probably tell from the table easily enough as well. X value of 25. Where did we have births per woman equal to 25? Well, down here at Costa Rica. So Costa Rica is an outlier. What do you do in this case? Well, that is a huge outlier. That is something we will totally want to omit from the data set. And realistically, why in the world would they have 25 kids per gal? That's not even realistic. 1 per year, you're looking at pumping them out from 20 to 45. That cannot be the case. Maybe there is a decimal error when they entered that data. So we're going to omit that data. Let's, as a result, because we know we're omitting that one particular outlier, let's describe the association with that omitted. So we're going to change our window here. We don't want to see all the way to the right. It makes it really tough to see this trend that looks to be negative and maybe linear when we're zoomed out so far from the cluster we care about. So by scanning through your births per woman, aside from that 25 data value, nothing exceeds 5. I will go window, X max, I will change to 5. We'll hit enter on that. We'll graph it. Now we've got a better analysis that we can run of the remaining data. Okay, so we've only changed the X max in the window so that we can see everything going on. The Y values are great. We can still see everything there. All right, so association. I'm not going to write these down. I would write these in your notes, though. We've got an association that in terms of the strength is somewhere between moderate and strong. It's clearly negative because as we increase the births per woman, which is your x-axis, the life expectancy is decreasing. And the form looks to be linear. Yeah, it kind of flares at the bottom. But so the strength between moderate and strong, direction negative, form linear. Okay, so there's part A. We're not going to reproduce the scatter plot in this area below. Are there any countries that do not seem to fit the overall pattern? Sure, we already mentioned them. Costa Rica has the life expectancy of 79 years for a birth per woman on average of 25 kids, which is ridiculous. So there's B. Find the correlation and interpret the value of R squared. Okay, so we're going to go to find correlation and R squared both. We'll go back to stat. Remember that linreg is the tool we need to find these things. We've got L1, comma L2. Your R value is 0.081275. Why is that positive when we just saw a negative trend? Well, because we've not removed the outlier yet. And we need to. We need to remove that from the data set. So let's go stat, edit, for the X value of 25. For Costa Rica is ridiculous. Did I pass over it? I certainly did. Where did I miss it? Oh, there it is. Okay. Let's delete that guy. And then the 79 tied with it needs to also be deleted. Let me double check that I deleted the right data values. Okay, so it's out of the data set. Now let's go stat, calc, linreg one more time. Okay. L1, comma L2. And there you go. There's a correlation coefficient of negative 0.81509, etc. We found that. It's negative, reflecting the fact that in the scatter plot, the direction of the points in the scatter plot went down. R squared is 0.664372. I will tell you the interpretation, but given that I've got 5 minutes in which I want to finish these notes, to keep them short and to beat the bell, I will tell you that this R squared of 66.437% means, again, we've talked about this in the first slide, or the second slide, depending on how you count, 66.437% of the variability in Y, in this case that would be life expectancy. 66.4% of the variability in life expectancy is accounted for by a regression line through these points, as long as we're going to make note of our exception here, as long as we remove Costa Rica from the data set, okay? Because obviously we used linreg before with Costa Rica in the data set. We got a very different R squared. So 66.4% of the variability in life expectancy is accounted for by a regression line, okay? Find the equation of the regression line in D. I'm going to use y hat and x here for the sake of expediency. In D, we've got y hat equals to blank x plus your y-intercept. Okay, what are the slope and y-intercept? Slope is negative 4.36. 4.36. Notice I'm using 3 non-zero digits. And B is 86.8. Okay. Did they say to interpret for this guy? Find the equation? Nope. Is the line an appropriate model? Describe what you see in the residuals plot. Okay, so we've done D. On to E here. Note, remember, because I use linreg, my residuals plot is already saved for me. I don't have to do anything additionally for that. So I'm going to go back to stat plot. Plot 1's on. We're going to leave L1 the same. You leave your X values the same because it helps to identify which residuals paired with which country when you do that. We're going to change L2 by going second list, scroll up. Normally you'll find resid right there. Change that. Zoom stat, and there you go. So in terms of whether or not the line is an appropriate model, both from the scatter plot that we looked at, ignoring the Costa Rica data pair, and from the residuals plot, we saw that nice linear form in the scatter plot. We're seeing an unpatterned residuals plot. That bodes well. So it sure looks like the line is appropriate based upon those two things, okay? And we had an R squared value of 66%. It seems like this linear model explains a lot of the variability in Y that we see, a lot of the variability in life expectancy. Okay, interpret the slope and y-intercept. Let's see if we can get these in 2 minutes. If our slope is negative 4.36, Okay, our slope m equals negative 4.36. Put that over 1. Consider the units. The x value here is births per woman, okay? So 1 birth per woman. For each additional birth per woman that you increase in x, you are predicting with this linear model a life expectancy that's going to decrease by 4.36 years. Okay? There is your interpretation of slope. The y-intercept of the line, remember, to get your y-intercept, you're substituting 0 for x. So that would say that if x is the births per woman here, which we're predicting life expectancy, your y, if a woman, or no, not really a woman because we're talking about countries, were a country to have 0 births per woman on average, this line would predict that there would be 86.8 years lived on average by the women in that country. Okay, so again, units are important. 0 kids per woman would predict 86.8 full years. All right, on average. G. If government leaders want to increase life expectancy in their country, should they encourage women to have fewer children? Explain. Okay, 2 things going on here that are in G, that are nested in G. First of all, we don't have any countries, and this is kind of a duh, we don't have any countries that have an average number of births per woman of 0. So clearly we are extrapolating below the lowest X value, the lowest births per woman value we have available, which is, trying to scan through this, 1.5. Yep. Canada seems to have the lowest number of children per woman. So we're going well beyond that lowest X value of 1.5, and that's not fair to do. Secondly, we can't know that there's not some lurking variable here, something that's hidden, not in the scatter plot, that's explaining this relationship between births per woman and life expectancy. Perhaps the births per woman is tied to affluence and healthcare, and maybe healthcare and affluence are really better predictors of a woman's life expectancy. Maybe births per woman is a byproduct of having more affluence. Maybe there's more to do than just pop out babies, as crude as that sounds. And with healthcare, and with affluence, rather, too, maybe women have jobs that are perhaps more intense, less family-based, who knows? But the bottom line is, again, that your scatter plot does not tell you enough about causation, cause and effect. You really only know about association. All right, there's your notes for the day.